Hi there, in this video we're going to continue our study of the derivative as a function. So this is part 3 of our video series. So we want to find the derivative of f of x equals the absolute value of x. And we want to know is the function differentiable on the entire real line. So in the last video I left with what does it mean to be differentiable? What do we mean by that? So for a function to be differentiable means the derivative exists at a point. So when we're asking if f of x equals the absolute value of x is differentiable on the entire real line, we're asking is it differentiable at every point of the entire real line? So let's look at the graph of the absolute value. The graph of the absolute value function is a v, so we want to know the derivative. We could try to use the definition of the derivative, but because we have the absolute value, that makes it a little bit harder, right? If I want to do f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h, it's a little bit harder to do when I have that absolute value there. I have to come back to the definition of the absolute value of x. What is the absolute value of x? Is x when x is greater than or equal to 0, or negative x when x is less than 0, and then do the derivative there. Or the other thing that I can do is say, well, I know that the derivative is the slope of the tangent lines. So what is the slope of the tangent lines here? So if I put any point, any xy point on this graph, if I draw a tangent line, notice that it follows this line all throughout. Every point here is already lying on its own tangent line, and this is y equals x. So what is the slope? M is 1. So that means that f prime of x is 1 when x is greater than 0. And what is it over here on the other side, right? This is our function x when x is greater than 0, negative x when x is less than 0. So this is the line y equals negative x. And what is the slope here? The slope is negative 1. So that means that f prime of x is negative 1 when x is less than 0. So I have the derivative is 1 when x is greater than 0, because we're following the y equals x line, so the slope is 1. And the slope is negative 1 when x is less than 0, because we're following the y equals negative x line. So then the question is, what is happening right at 0 for the derivative? So let's graph the derivative. To graph the derivative, I need to graph the line y equals 1 when x is greater than 0, and the line y equals negative 1 when x is less than 0. So we have that graph right here. So this is the line y equals 1, and this is y equals negative 1. So this is our graph of f prime of x. So the question is, what is happening at 0? Now notice that going back to the definition, we said f is differentiable if at a point, if the derivative exists at that point. And so, right, f of x here is differentiable at a point if the derivative exists at that point. Does the derivative exist at x equals 0? Can I have a tangent line? No, right? There's no, the function is not even defined there. So therefore we cannot have or there's a big jump, so it's not, so we cannot have the derivative. So we say f of x equals the absolute value of x is not differentiable at 0. Because I cannot have a single tangent line, so the slope at 0 looks like the slope could be 1 and the slope could be negative 1. So going back to my absolute value, notice that if I try to draw a tangent line here, I could draw many different tangent lines. So I could have a tangent line that goes with the slope of 1, with the slope of -1. I could have all kinds of different tangent lines, so there's no unique tangent line. So we say that f prime is undefined, right? Because it's not defined to be a unique answer. It can be many, many things, so it's undefined. So f of x is not differentiable at x equals 0. Therefore, f of x is not differentiable on the entire real line on minus infinity to infinity. What we could say is that it is differentiable on different intervals. So I can say it's differentiable on negative infinity to 0 and then 0 to infinity, just not at 0. But everywhere else, I have a tangent line. There is a slope for the tangent line at that point. So what does it mean to be differentiable? That means we can draw a tangent line there and find the slope of that tangent line. And so we have three different ways to tell if a function is differentiable. Or I should say not differentiable. So a function is not differentiable if it has a corner. So in this case, in the first picture, we have a corner. So this is, then f of x is not differentiable. So let me say ways to tell a function is not differentiable. So when you have a corner, when you have a discontinuity. So in this case, I drew a jump discontinuity, but it could also just be a removable discontinuity. So as long as there is a discontinuity, you're not going to be able to have a tangent line at that point if the point is missing. And in this case, right, you have a jump discontinuity, so definitely not differentiable. And then if you have a vertical tangent line, so that will make it so that the slope is undefined. So then there's no derivative there. The derivative is undefined. So these are three different ways to quickly tell if a function is not differentiable. So a corner, a discontinuity, and then a vertical tangent, or if you have a vertical asymptote also, but then that likely means you have a vertical asymptote, that value is not in the domain anyway. So back to our absolute value, right, that is a corner. So this is, visually we can see that's why it's not differentiable. So let's try a couple of examples. So let's look at this example. Determine the intervals where the function is differentiable. So looking at x plus 1, it's a polynomial, it's a line, so differentiable. X squared minus 2, quadratic, I can find the derivative on the entire real line. So we have a risk of this not being differentiable at 1. So let's take a look at the graph and see what happens here. So when we graph when x is less than or equal to 1, we look like the line y equals x plus 1. So that's this line, y equals x plus 1. And when x is greater than 1, right, this is our 1 here, we look like the quadratic. So this is y equals x squared minus 2. Notice that we have a discontinuity there. So we can say then at x equals 1, this is not differentiable. So we can say then f of x is differentiable everywhere else but that point. So it's differentiable on, it asks for intervals, so I better give it intervals. So minus infinity to 1, and then 1 to infinity. So that's where it's differentiable. Our next example, let g of x be this function, and notice that at 0, we're going to get -1. So the function I can see that is going to be continuous, but does that mean that it's differentiable? So let's look at the graph for this function. And this is what it looks like. So at 0, what is happening? And notice that we have a corner there. We have a little kink in the graph. So this is a, oops. So we have a little corner there. So therefore it is not differentiable at x equals 0. So we can say f of x is differentiable on minus infinity to 0, union 0 to infinity, right? We have a corner there, so we won't have a uniquely defined tangent line. So then the function is not differentiable, which brings me to a very important theorem that says if a function is differential at a point, then the function is continuous at a point. If a function of x is differentiable at a point, then f of x is continuous at a point. Now this is not differentiable, it is continuous. So then that brings me to a point of caution, right? What we want to say is that the converse is not true. If a function is continuous at a point, it does not imply the function is differentiable. Think of the absolute value of x, or this is a good example also. This function is continuous at 0, but it is not differentiable because we have a corner there.